In the world of electronics, there's this tiny little component that's kind of part amplifier, part calculator, and even part decision maker. It's called the operational amplifier, or op-amp. And believe me, it's the secret ingredient that lets our gadgets perform some real mathematical magic with just electricity. So let's dive in and see how this thing actually works.
Okay, let's start with a kind of a wild idea. What if you could actually perform calculus, not with a pencil and paper, but with a tiny electrical circuit? I know, it sounds like science fiction, right? But that's exactly the kind of power that's hidden inside the chip we're going to talk about today. And here it is. This is our hero, the operational amplifier, or op-amp for short. Now, I know it just looks like a triangle on a diagram, but this simple shape is genuinely one of the most powerful building blocks in all of electronics. We're about to see how this one little symbol can be used to add, subtract, compare signals, and yeah, even perform the calculus we just mentioned. It's pretty amazing.
So here's our game plan. First, we're going to look at the op-amp as this perfect, almost magical device. Then, we'll get our hands dirty and see how it works in the real world with some basic circuits. After that, we'll check out its nonlinear side, and finally, we'll peek inside the black box and see what really makes it all tick.
All right, first up, the perfect amplifier. See, to really understand how to use an op-amp, engineers have this clever trick. They start by pretending it's a perfect, ideal device. Now, this isn't actually true in reality, of course, but it's an incredibly useful starting point that lets us get a grip on the core concepts without getting bogged down in the messy details. So, what does this perfect amplifier do? Well, for starters, it has infinite voltage gain. That means it can make any signal infinitely stronger. It also has infinite input impedance, which is just a fancy way of saying it can measure a voltage without affecting the circuit at all. It's like a perfect spy. Then there's zero output impedance, so it can deliver all of its power perfectly to whatever's next in line. And finally, it has infinite bandwidth and an infinite slew rate, which basically means it can amplify any signal at any speed instantly. In short, it's a perfect, almost magical black box. Of course, in the real world, nothing is ever perfect. So here, you can see our ideal model compared to a real-world classic, the 8741 op-amp. Is its gain infinite? No, but it's about 200,000, which is massive. Is its input impedance infinite? Nope, but at 2 million ohms, it's incredibly high. And the output impedance isn't zero, but it's still really, really low. So the main takeaway here is that while the perfect op-amp doesn't exist, the real thing gets so close that our beautiful lie of the ideal model is actually an incredibly useful way to think about it. Okay, now let's see how this all comes together. Welcome to op-amps in action. I want you to think of this section like a recipe book. By adding just a few simple components like resistors, we can make our op-amp do all sorts of predictable mathematical things. Our first recipe is for the inverting amplifier. This is one of the most common op-amp circuits out there. We start by feeding our signal into the negative input. But here's the secret sauce. We add what's called a feedback loop. We just connect the output back to that same input with a resistor. This feedback is what tames that insane power of the op-amp and makes it do exactly what we want. Then we just connect the positive input to ground, which is just our 0-volt reference point, and that's it. Our circuit is complete.
So what does this super simple recipe actually give us? It gives us an amplifier where the gain, how much it boosts the signal, is set just by the ratio of those two resistors. It's beautiful. For example, if that feedback resistor is 10 times larger than the input resistor, our signal gets amplified by exactly 10 times. That minus sign just means the output wave is an upside-down or inverted version of the input. It's just that simple and totally predictable.
And this visualizes it perfectly, doesn't it? A small input signal goes in, and a much larger inverted output signal comes out. By using that clever little feedback loop, we've taken an almost infinite gain and we've tamed it to create a precise, totally controllable amplifier. Okay, on to recipe number 2. Let's take that exact same inverting amplifier circuit we just built, but this time we're going to make one tiny change. We're going to pull out that feedback resistor, R2, and we're going to replace it with a capacitor. That's it, just one component swap. With that one little change, the circuit's function is completely transformed. It's now an integrator. You see, a capacitor is kind of like a tiny bucket that stores up electrical charge over time. By putting it in the feedback loop, the circuit's output now represents the accumulation of the input signal. And that, my friends, is exactly what integration is in calculus. If you feed in a square wave, you get a triangle wave out. We are literally doing calculus with a chip. How cool is that? So far, we've been in the linear world, where everything is nice and proportional. But op-amps are also masters of the nonlinear. This is where we stop doing math and start making decisions with electricity. Our next recipe, the voltage comparator, is even simpler than the last one. We just feed a steady reference voltage into one input and our test signal into the other. And here's the key. Notice what's missing. There's no feedback loop. By getting rid of it, we're using the op-amp open loop, which means we are unleashing its full, untamed, massive gain. So what does it do? Well, with that enormous gain unleashed, even the tiniest, slightest difference between the two inputs makes the output slam all the way to its maximum or minimum voltage. So if our input signal is just a little bit higher than the reference, the output goes high. If it's even a hair lower, the output goes low. It's a high-speed electrical decision maker. This simple circuit is basically the fundamental bridge between the smooth analog world and the crisp ones and zeros of the digital world. Okay, so for our last section, let's finally go inside the black box. We've seen what this magic triangle can do, but what's actually in there, making it all work? How do we get from a bunch of simple transistors to what is, for all intents and purposes, a tiny analog computer?
Well, the secret ingredients, as you might have guessed, is the transistor. It's the fundamental switch that powers all of modern electronics. An op-amp isn't just one thing. It's an incredibly intricate circuit. A small army of transistors all working together, each with a specific job to achieve that near-perfect amplification we talked about.
And this technology didn't just appear out of nowhere. The basic idea was patented way back in 1925, but it wasn't until 1947 that Bell Labs built the very first one that actually worked. But the real game changer was the MOSFET in 1960. This was the transistor that could be shrunk down and packed by the dozen onto a single piece of silicon. And that's what made integrated circuits like our op-amp finally possible.
This right here is what bridges that gap from the drawing board to the real world. Whether it's in the old-school metal can or the modern plastic package, this pinout diagram is like a Rosetta Stone. It shows you how that abstract triangle symbol connects to the physical pins of the chip you can hold in your hand. Pin 2 is the inverting input, pin 3 is the non-inverting, pin 6 is the output. This is what lets an engineer or a hobbyist actually use one of these things. Let's just pause on this number for a second. 200,000. That is the raw, untamed, open-loop gain of a typical 741 op-amp. To put that in perspective, a 1 microvolt difference at the input, that's a millionth of a volt, could create a 0.2-volt output. It's this immense, almost uncontrollable power that we have to tame with feedback to create all those useful circuits we looked at. And here it is. This is what's actually inside that simple little triangle symbol you see on a schematic. This entire complex circuit, all these transistors, resistors, and capacitors, is intricately etched onto a tiny piece of silicon. And that is the true magic of the integrated circuit, taking all of this complexity and hiding it behind a simple, powerful, and incredibly easy-to-use component. And, this quote from a university physics lab manual really just sums it all up perfectly. Op-amps are highly versatile and have numerous applications. From doing basic math to performing calculus and making logical decisions, they really are the Swiss Army knife of analog electronics. So we've seen how this one little component, when you combine it with a few resistors and capacitors, can perform incredibly complex mathematical tasks. It's a true building block of modern technology. Which leaves us with a final, really tantalizing question. If just one of these chips can do so much, what becomes possible when we start connecting hundreds, thousands, or even millions of them together?